You may have noticed I'm not Joe. My name is Allison Farish. I'm a MPP in 674. I'm starting to help out with the Goddard Exoplanet seminars. And our speaker today is Ishan Mishra, a PhD candidate at Cornell University's Department of Astronomy, primarily focusing on planetary spectroscopic retrievals. This involves analyzing spectroscopic data from planetary surfaces and atmospheres using appropriate physical models and statistical tools to infer properties like composition, temperature, and etc. of the planetary body being observed. The scientific area of focus for his thesis work has been Europa, and he's going to describe a spectroscopic retrieval framework that can help tease out signals of trace and spectrally complex species. And he's worked also in a few exoplanet science projects. But with that, I'll let Ishan take it away.
Thank you. Yeah, let me just reshare my screen. Sorry, something went wrong. Oh, can you see my slides?
Yep, looks good.
And can you hear me clearly?
Yep, all good.
Perfect. Well, thank you, Alison, for the introduction. And hello, everyone. I am Ishan, and today I'll be talking about my main thesis-related project on providing new constraints on Europa's surface composition. And I know that the talk abstract said that I'll also be giving an overview of a project related to characterizing rocky exoplanet surfaces, but the results are not quite there yet. And since I'm not the PI of the project, I decided against including it in this talk, but I hope my Europa work is interesting enough. So yeah, let's get started. So outline of my talk is going to be basically, I'll first sort of provide an overview on Europa's composition and just make a case for why we're interested in characterizing its surface composition. Then I'll be talking about a new framework that I'm developing to analyze the spectroscopic data using Bayesian inference, which I'm sure a lot of you are familiar with since it's used very widely in exoplanet science. And that is basically where we got the, because one of my advisors is an exoplanet scientist, we decided to sort of adapt it to the Europa problem. And then finally, I will talk about some applications to Europa from my own work from past and current projects. So why the interest in Europa's surface composition? You must know Europa is famous for having a subsurface ocean, salty ocean, and salty liquid water ocean. And from all our understanding, it is probably a good habitat similar to the deepest parts of our own ocean on Earth. And so hence it's a prime astrobiological target. So like if in the schematic, you can see like we believe that there is a rocky mantle which is in contact with a salty water ocean. And just like what we found in Enceladus from the plumes, we have evidence for hydrothermal activity. We believe something similar can happen on Europa. And so like the environment is perfect for life as we know it on Earth to exist and thrive there. So is there another sort of origin or origin of life that has happened there? That's like the big overall science question that NASA has prioritized and is the key driver for most of Europa research. But before, like the ideal thing would be to go into the ocean and like explore it directly, like for Europa, Enceladus, and any of the ocean worlds in the outer solar system. But we are looking at a tens of kilometers thick ice shell that we need to penetrate, and the technology is not there yet, and hopefully it can happen in my lifetime. But meanwhile, our way to sort of understand the ocean is to see its expression on the surface. And so there are geological features, and Europa's young surface, basically lack of craters, tell us that there is an active exchange between the subsurface ocean and the surface. We have tentatively detected evidence of plumes. And in the previous figure, you can see like the cracks in tectonic almost features on the surface of Europa are correlated with with composition. So that pointing to maybe like these areas being dominated by endogenic material coming from inside. And so this endogenic material is basically what we're interested in. So the material that has come up from inside, either over a long time in like these geological regions, or fresh, or very recently from plumes-like extrusions, and we want to characterize the composition of that material, and then use that to constrain the composition of its subsurface ocean, and consequently understand its potential for habitability. But Europa is in such a sort of a dynamic environment because Jupiter's magnetosphere is constantly bombarding it with a lot of charged particles. Then there's of course like impacts from micrometeorites, and that is more than what we see here on Earth because of Europa being airless. So there's a lot of external factors that are also modifying the composition. So keeping those two things in mind, the goal is to get at the endogenic material and understand its composition. To just give you a quick primer of what we know exists and what we have like definite sort of evidence for on Europa's surface. So firstly, there is a lot of water ice. So this figure basically shows a map of the two forms of water ice, amorphous and crystalline. And Europa has both because it's in this interesting regime where the temperature is hot enough at certain portions that it favors crystalline ice, but then you are getting bombarded by charged particles, which destroy the crystallinity and make the ice more amorphous. And so you kind of see both forms being present on Europa's surface. Then we have a lot of salts. So in this figure, the bold line is showing Europa, actual spectrum of Europa, and the dotted line is basically a model that is a mixture of a simple linear mixture of different kind of sulfates, hydrated sulfates, and the general nature of the spectrum and the general features of the water band sort of matched our expectation from hydrated salts, and the reason there are like a lot of sulfates primarily is because, and also there is hydrated sulfuric acid that has been detected and also sort of shown from lab experiments to be a dominant component on your surface, is because Io is spewing out a lot of sulfur, and that gets trapped in Jupiter's magnetosphere, finds its way to Europa's surface, primarily on the trailing hemisphere as Europa is orbiting. So its back sort of trailing hemisphere gets most of the bombardment. And so there's a lot of sulfur, and so sulfur products. And those are the sort of decide the bulk spectrum, so the bulk continuum of the spectrum. And then oxides have also been detected. So these like some sharp features at longer wavelength, but the detection has been tentative. But we also see some features in the UV and visible. And oxides are also expected because the surface is primarily dominated by water ice. You're getting the water is breaking up because of bombardment by energetic particles, and so like those or whatever reactions follow leave oxides as like one of the as many oxides as like the byproducts of those reactions. And more recently, there was this exciting discovery of sodium chloride on Europa's surface. So sodium chloride, and what was interesting was that sodium chloride is spectrally very flat when you just look at it, just look at like a regular sample of sodium chloride, but when you irradiate it with charged electrons, it develops new features called color centers. And so that is basically what was detected using the Hubble Space Telescope. And what more interestingly, it was detected in regions that are geologically younger. So it mapped pretty well to those regions. And so pointing to probably a sodium chloride coming from the interior, which would make the ocean more similar to ours. And all the data that I showed you in the previous slide is reflectance spectroscopy, which is like a primary tool to understand surface composition in the solar system in general, and especially for Europa, because most of the missions that have collected data of Europa had a near infrared spectrometer. Then we have gotten a lot of data from the ground, and most of the fundamental like sort of vibrational modes of molecules exist in this region. So hence it has given us the most information. But inferring composition is challenging. It's not as simple as like looking at like identifying pictures and trying to fit your expectations there, because there are many things that are making the problem difficult. Because firstly, most of the Europa's like bulk spectrum is basically just like looks a lot like water ice, and how it deviates is basically distortions of its water band. So there's 1.5 and 2 microns are the two big water ice bands, absorption bands. And when you have hydrates, so like when you have salts and water molecules attached to the salts as water of hydration, the primary effect in the near infrared is to kind of distort the water ice band. And because many of them can distort the water bands in a similar way. So at the resolution that we have had spacecraft data so far, it's difficult to tell them apart. So like sulfuric acid alone works well, whereas like some mixture of different salts also produce similar fits. So yeah, it's a degenerate species basically. Then there's another effect that we see, which is shifting of spectral bands due to irradiation. So your water ice shell around your hydrated salts are getting distorted because of irradiation, and that sort of changes the fundamental energy levels and shifts the band. And so this has been seen in the lab. This is also seen in the Europa data. So it's something to be taken into account when we are trying to find or detect species and get at their abundances. And something that I mentioned, which is like formation of new spectral features. So this is sodium chloride. When it's not irradiated, and as you continue irradiating it, you see that these deep features develop. Yeah, this like so more and more lab work is showing that for different kind of salts, this is something that can be used as an identification feature. And once you have identified species, once you have your sort of candidates for what you're seeing, the next thing we want to do is want to get at the abundances. So how much of what is present, and for that we rely on modeling the reflectance spectra. So we're fitting the data with a model, and the model is not just is not just incorporating like the effect of the different amounts of different species present, but also physical parameters like grain size of the regolith, porosity of the regolith. Because as shown in this GIF, grain size is an interesting parameter where it changes the absorption feature strength and also shapes, and hence becomes degenerate with the abundance. And so it needs to be taken into account when you are doing the fits, so that you have like correct estimates or like conservative estimates on your abundance. So specifically from the spectroscopic, from a fitting analysis point of view, where we try to get at the abundances, we wanted to sort of revisit look at the Europa data with a tool that would allow us to sort of systematically answer two things. Also because like there are so many different candidate species, there are there's degeneracy between them. A lot of them look similar. And then also we want to, like I've talked about the bulk components on Europa surface, but of great interest to the community is like trying to go at more trace species, so like organics and things like that. And so to do that, to get that information out of the data, we went looking for a framework that would allow us to systematically answer two things. Firstly, is there significant evidence for species X in the presence of all possible candidates? So like, especially if like the there are overlapping spectral features between different species, whose evidence is the strongest, like which one of them is the best candidate. And then and also allowing for the effect of physical parameters that are this grain size and porosity of regolith. So even when you're controlling for those parameters, does the evidence stand? And if there is a significant evidence for presence of species X, then what is the abundance? So like once you know, eventually you have confirmed that, okay, this is our best candidate or best hypothesis, then can we tell something about its abundance? And what are the confidence intervals on that value? Because that is also something that needs to be reported, because a lot of time your constraints that you're getting on your abundance are not very sharp. And so especially like if you're there's a lot of degeneracy between the parameters, or your data is just of low quality, the confidence intervals matter. So one of the methodology is Bayesian inference, and to very simply, it's fitting a model to the data. So we have our data, our model, which I will describe shortly, is the Hapke reflectance model, which is a popular model in the solar system community to model the reflectance of planetary surfaces. And when we use a Bayesian inference framework to fit this model to the data, we get out two key outputs that we are interested in for our work. So firstly is the parameter estimation that mostly people are familiar with, that it helps us explore the parameter space efficiently and get posterior distributions of our parameters. Model comparison is something that can help with finding the right set of species that work best for your fit, or like sort of evaluating the evidence for a given species. And that is something new that we have tried to bring into the Europa data analysis work. So let me first briefly describe the forward model. So the forward model is basically an analytical approximation for the reflectance from the surface. So this is the geometry. You have sun, you have your surface, you have an observer. Here, it could be a spacecraft, ground observatory on Earth, a space telescope, and the incidence, emission, and phase angles. And your overall reflectance. So IF here is basically solar flux, and I is the irradiance you're receiving. It's just like a unit, dimensionless unit for reflectance. It depends on among the observation geometry parameters, along with them, sorry. It also depends on, like, a key parameter is single scattering albedo. So single scattering albedo basically governs how your average particle of a species is absorbing light as a function of wavelength. So single scattering albedo fundamentally depends on the refractive indices or the absorption coefficients of your species. And when you have many things in the mixture, if your regolith is made up of many things, as is true for solar system surfaces or any planetary surface, you take sort of a weighted average. So you're based on the fraction of your given of your species, its cross-sectional area, and something called the extension coefficient, which is assumed to be the same for most species. So you get a sort of an average single scattering albedo that goes into your equation here. And then I described the observational geometry parameters. Then phase function of a material is basically describing how it scatters light in terms of directional scattering. So whether it's preferentially forward scattering, backward scattering, isotropic scattering. So it just describes that. And just like for single scattering albedo, if you have different materials that have different scattering properties, then you will get like a weighted average for the average phase function. H is a Chandrasekhar integral function associated with like multiple scattering in the material. So it just approximates a photon getting like scattered in a semi-infinite layer and how that works. And K is the porosity coefficient. So the porosity of your material, so how fluffy it is versus how densely packed it is, also influence the reflectance. And so it's a direct multiplicative factor. So a lot of parameters, but it's a huge legacy in the solar system science, and does a pretty good job in approximating the reflectance that we see. So yeah, so that was our model. Let me talk quickly about the framework. So firstly, like parameter estimation. So so with your preferred model, what you're trying to do is basically estimate its parameters. So this is the famous Bayes equation. So you have your posterior probability on the left-hand side, your which is basically a function of the likelihood and the prior. And there's this normalization integral, which for parameter estimation is not important, but for model comparison, it becomes important, as I'll describe later. But what we are trying to do is basically, if we have so for example, like this blue dots represent a data set, and this green line is like the maximum likelihood model or the best model. And if you're describing this model with two parameters, so this is like the parameter space, and the X point marks your maximum likelihood solution. So that is like the peak of this posterior function. And what the Bayesian algorithm is going to do is going to try to map this posterior function. So create sort of like collect samples that are described by this posterior function. So it will basically go around and just collect samples, and these samples, like some of them will fit the data very well, some of them will not. So they're deviating further and further away from, like, so they're lower probability basically. So if you imagine like a 2D space, then this posterior function is basically a hill, and we're trying to map that hill. So once that process finishes, you get something like this, where your 2D collection of samples, you have your collection of samples. In this case, it's two-dimensional. And then when you normalize it or marginalize it, sorry, along specific dimensions, you get your posterior distribution. So in this case, our two parameters, we get distributions for them. From that, you can get your 1 sigma, 2 sigma constraints, or whatever statistics you want to do with it. And so this is simply the how parameter estimation works. And here I'm just showing an example from my first paper, where we like tested this like the Haki model with this Bayesian framework on a laboratory data of water ice. And this is basically showing our maximum likelihood model, which does a pretty decent job in fitting the most of the aspects of the spectrum. But there are, of course, like some deviations which are due to like just like the limitations of the model, because it is a simple analytical approximation. So for example, it will just assume one average grain size, whereas in reality, when you're looking at lab samples, there's a distribution of grain sizes. And then also there are errors in the inputs to the model, which is basically the refractive indices of water ice. So there were some errors there. So not the best match, but broadly it is doing a pretty good job. And especially constraint, our goal was to constrain the grain size, and we got a pretty good constraint, accounting for degeneracy with two other parameters. So this is porosity, and this is like an uncertainty on the error of the data, because that was not well characterized. So we let that be a free parameter as well. And we got pretty good constraints, and the value that we were getting, like the median value, was also close to what was cataloged for the sample, like in terms of like average grain size. So it's pretty decent. So now moving on to model comparison. What is that? So model comparison is like this other thing that the Bayesian framework gives you. So when you're mapping, so for a given model, when you're trying to map the posterior function, the normalization integral is something called the evidence. And that is basically the total probability of the model, given the, like it's related to the total probability of the model, given the data. And how it works is basically that, and how we use it for our a purpose of evaluating the evidence for a species is basically this, where first we take model 1, which is a model with all our species of interest, including like our species X for which we are evaluating evidence. So this will basically be our sort of reference model. So it will have all the candidates we think we are seeing in the data or we want to evaluate the evidence for. So we'll throw all of them together. And in the second model, we will basically knock out the species that we are interested in evaluating the evidence for. So this will be basically n minus one species. And then we compare how both models fit the data. If model one, which has all the species, including species X, does better than model two, which does not have species X, then we'll conclude that, okay, species X is needed even in the presence of everything else to explain the data. So that translates to like some degree of detection significance. And on the other hand, if model two does better than model one, that means that that species X, knocking out species X actually helped. And so it's not really needed. And so we and conclude that, okay, we don't find any evidence for it. And doing this for all your candidates will lead to like acceptance rejections for them. And you will be left with a subset of species that sort of best explain your data via this methodology. To show you an example of this, here I have a reflectance spectrum that has that's a mixture of three minerals: olivine, enstratite, and anorthite. And in these curves below, I'm showing their individual contribution to the spectrum. So it's basically their reflectance is multiplied by their abundance fraction. So anorthite, as you can see, is the weakest sort of contributor, while as olivine and enstratite are strong contributors. So when we do our systematic analysis, basically we first start with a model that has all our candidates. So we say that, okay, we are seeing a big enstratite feature here. We are seeing like an olivine feature over here, and so we just basically pick our candidates, and enstratite feature is not clearly visible, but there's like a small dip here. So we pick our candidates, we do our analysis, we get some metric for the evidence for this model. Then we systematically knock them out one at a time. So first we knock out olivine. We see that the evidence decreases significantly, meaning that olivine was it's very much needed, and that translates to a very high detection significance for olivine. Similarly, when we knock out enstratite, evidence decreases much more, translates to a high detection significance for enstratite. And when we finally knock out anorthite, evidence decreases, but not as much, but that still translates to a strong detection for anorthite. And the reason that it works so well in terms of like if getting the evidence for this like trace species or like of a species that is contributing weakly is because anorthite has a feature over here, but it also is contributing to the overall continuum of the spectrum. So you see that it is there is some sort of nature to the anorthite spectrum, and that has an effect on the total spectrum. And so because this via spectral fitting, you're trying to evaluate or assess the effect of every species at all wavelength channels. So like all of them, not just where the feature is. It kind of strengthens the detection. Okay, so now that I have presented the framework, shown some examples of the kind of analysis we are doing, let me present some applications to Europa. So the first application, or the first project I'll talk about is analysis of some Juno observations of Europa. So Juno is currently studying the Jupiter, well, primarily Jupiter, but also taking observations of its satellites. And in 2019, it collected a lot of data of Europa. So these regions are basically showing where the data was collected from. And this is kind of an example of the kind of data. So especially if you compare it to the NIMS, which is the NIMS is the Galileo spectrometer and GERAM is the Juno spectrometer. So if you compare the two, the GERAM data was very noisy, and especially unfortunately, it was quite noisy beyond 3.5 microns, which has been a region that has not been well studied because even Galileo data was very noisy beyond that because reflectance is very low. The detector is more susceptible to like irradiation damage. And so it's just data is just not good. Then the same held true for Geram. But still, we wanted to, like, there's a new data, wanted to analyze it. And so we dug into the data set. Unfortunately, when we started this project, which was right after the day the data was first collected, most of the spectra did not have well characterized location. So basically, for example, like here, this says like the data collected in the 81st orbit of Juno. We knew that the spectra, like maybe like 100 spectra came from this region, but we did not know which spectra came from where. So the exact pixel location was not determined, and consequently, the observational geometry parameters were not constrained. So we did not know what was the incidence emission angle. There only one sort of subset of spectra had like decently characterized location. So that's why the box is very small. And so we decided to just focus on them. So it's coming from this equatorial region, sort of a from the like the leading hemisphere of Europa. And so this figure is basically in the triangles, you're seeing the spectra. The spectra is very noisy, like all of them. So we just like looking at the mean. And so this purple dot is basically showing the mean of all the spectra. And we decided to look at this data and primarily characterize the composition of water ice. So what fraction of the two types are present there? So because as I'm showing in this figure, from previous Galileo NIMS data, we have seen both forms of water ice. So the spectroscopy features are visible, but we have no work had been done to sort of get at the abundance. So like how much of the two is present, and so that was the goal for this project. So we basically wanted to constrain the abundance and grain size of amorphous and crystalline ice. And secondly, we wanted to compare intimate versus linear mixing models' ability to fit the data. And so what does that mean? So when you're looking at a planetary surface, you can think of it as being like existing in sort of two modes. Firstly, the species can be very, like whatever is present on the surface, different chemical species, they got very well mixed together. So that is called intimately mixed. And secondly, you can think of them as, and so in the first case, so the overall reflectance is basically like comes from, it's a non-linear sort of a mixture of the individual species reflectance or their single scattering albedo, whatever. So the contribution is non-linear. But on the other hand, you can think of the planetary surface as being like distinct patches of different materials. So like in this area, there is some, like, I don't know, some kind of, so water. In this area, there is more salts, and this area, there's something else. And so when you're looking at the total reflectance from that area, it can be approximated as a linear sum of the reflectance of the individual species weighted by how much their area is. And so that is a linear mixed model. That is a linear model. And so these two different modeling basically correspond to two different like physical state of the material of the surface you're seeing. And so we wanted to see which one is preferred. And here's the key result from our analysis of that mean Juno spectrum. As we compare four models, the first is like the two of them, two kinds of water ice intimately mixed together, so they're well mixed. Secondly, they exist as different patches. And the third and fourth models were just one component each. So the second kind is not present. And this is the key, like sort of that model comparison metric, where what you're seeing is basically these numbers are telling you how much more is the reference model preferred over these models. So it's like a ratio of the probability of this reference model over the other model. So the larger this number is, the more the reference model is preferred. And so you can see that clearly the intimate mixing model was preferred, had a very high significance as compared to linear mixing versus or the individual or the one component only models. And for this preferred model, the results that we got for our parameter estimation are shown here. So the parameters that we were fitting for was the grain size of the two kinds of water ice, fraction of one of them because the other one is dependent, 1 minus f, and the porosity. And so what we got was basically small sized grains, so like around 50 microns grain of amorphous ice, very large grains of crystalline ice, very large amount of amorphous ice, and a very highly porous liquid. And these results roughly agreed with what had previously been seen, mainly that amorphous ice is very dominant on Europa's surface, especially at lower latitudes where the radiation processing is higher. So especially the very top layers where reflectance spectroscopy is probing the surface, you get a lot of amorphization. And porosity being low is also something that has been previously seen from like polarimetric studies of Europa's surface. So that was good. But one problem we were facing is that so this, I'm just here highlighting, like first one thing was of course like that some of the data set was just not agreeing with our some of the wavelength regions were just not agreeing with our model. But even in the regions where the model was agreeing, our model was giving a good fit to the data, the scatter in the residuals, so like this is basically showing like the standard deviation of the residuals in these regions. It was much higher than the noise on the data. Which indicated that, okay, maybe the noise is underestimated probably, because like if you have, if everything is as expected, then the scatter in your residuals is on the order of the noise on your data. But this was off by like an order of magnitude or more. Since GRAM data or the Juno data had a lot of calibration issues, like for example, you will see that the data we are using is normalized at 1, we're normalized to this like 1 at this wavelength because there were calibration issues. The noise was also not well characterized. And so I took this as like an indication that, okay, noise is underestimated. So we proceeded to just inflate our error bars and see how that affects results, like assuming that our noise is underestimated, what would happen? So we basically tried a range of inflation parameters consistent with how much this difference is. And our results were pretty consistent. So the intimately mixed model was preferred for all cases, and the maximum likelihood solutions were also pretty much the same. So like that was good. That like even though the review of probably working with underestimated errors, it was fine within within our idea of how much that and how much the factor was of underestimation. And of course, like as I pointed out, there were regions where the model was just not fitting the data well. And I mean, it's the work in this work, we assumed we were just working with 2 forms of water ice. We had not we're not taken into account like the other things that I had mentioned, like salts and sulfuric acid and stuff, mainly because we wanted to sort of keep the analysis simple. But on the second hand, the absorption coefficients or the refractive indices that we need to model all those species do not exist in the literature beyond 3 microns. And like, actually beyond 2.5 microns. So both of these regions of mismatch, we could not really go ahead and model. But hopefully, like when that lab data comes along, I'll get to revisit these spectra and try to understand what is happening here. Okay, so now we'll move on to the second project that I worked on, which was revisiting select Galileo spectra. So Galileo is has been a primary data source for Europa. It collected a lot of good data, and what we wanted to do was basically take 3 sort of archetypal spectra from Europa surface and then analyze them in a comprehensive way, unlike it had been done before. And so I'm showing here where those 3 spectra are coming from. So S1, S2, and S3. So S1 was coming from this very visibly dark part of Europa's trailing hemisphere, so where most of the irradiation damage exists and most of the non-water ice material is thought to be present. And then S2 and S3 are coming from just outside these regions, but from different latitudes. And this is what those three spectra look like. So the data was within 1 to 2.5 microns, where most of the Galileo data resides, because beyond, even though the spectrometer extended till 5 microns, the data is very noisy and it's mostly unusable. So our goal was to try to do a spectral fitting analysis of the spectrum using 5 components. So the 2 forms of water ice is obvious, because it's a water ice is a bulk component on everywhere on Europa. Acid hydrate, so this was sulfuric acid hydrate. And as I had mentioned, like sulfuric acid is something that is thought to be the primary component of regions where most of the sulfur bombardment is happening. So basically like the trailing hemisphere of Europa, and theoretical estimates or laboratory experiments show that when you bombard water ice with charged sulfur particles, the reactions that happen result in sulfuric acid hydrate as one of the dominant equilibrium products. And so that's why we chose that as like the non-water ice component. And then carbon dioxide and sulfur dioxide were 2 trace oxides that had been detected tentatively on Europa's surface, but no estimation for their abundance had been obtained from the spectroscopic data, so we wanted to do that. Yeah, so here I'm just showing like the absorption coefficient or proxy for absorption coefficient, which is the imaginary part of refractive indices for all our candidates. And the reason I'm including this is just to highlight that carbon dioxide and sulfur dioxide do have a lot of sharp features in this wavelength region. We don't really directly see them in the Galileo NIMS data because like the bulk components are just orders of magnitude stronger. So like the water ice and sulfuric acid hydrate here. But we still wanted to include them in our modeling analysis, but because the point is to like have all your candidates that you think are present and systematically find the best subset that works. So sulfuric acid hydrate, as I was mentioning, in a very sort of early analysis in 2005, where it was like people were just trying to fit the data with one kind of water ice and sulfuric acid hydrate. They found, and they created this like map of the trailing hemisphere of Europa. They found that the sulfuric acid hydrate abundance correlated very well with the sort of the dark parts of Europa. So you can see like this dark region specifically with this like sort of tail kind of feature is also seen in the abundance, high acid hydrate abundance distribution from the older work. So yeah, so like there was one other previous work that had seen evidence for this. Carbon dioxide and sulfur dioxide, weak features in the longer wavelength. So some of the few spectra that were good from Galileo, they could see like maybe hints of, not so much for sulfur dioxide, but carbon dioxide. And for this paper specifically, which is the seminal work in for trying to find these 2 oxides, they analyzed this region. So there were significant parts of the trailing hemisphere where they found carbon dioxide and weakly sulfur dioxide. So what were our results? So firstly, and this was the most expected one, which was like a very high detection significance for acid hydrate. So in all 3 spectra, we found that acid hydrate was strongly present. And in S1, which was coming from the darkest parts of out of the 3, acid hydrate dominated completely, like greater than 99.5% abundance, slightly lesser in the other 2. As for water ice, in S1, we found that there was weak evidence for water ice, and both of them kind of work. So the abundance was just too low to tell them apart. Whereas in S2 and S3, we found very strong evidence of crystalline ice. And that is because like crystalline ice has this strong 1.65 micron feature that you can clearly see in the S2 and S3's data, and it's missing from S1. So that's why like we're expecting it to be come out at a high significance. Not so much for amorphous ice, which was detected at lower significance. And what we think is happening here is that like the reason that maybe S2 and S3 are showing very strong evidence for crystalline ice, whereas S1 is not, is probably because S2 and S3 are coming from regions that are further away from the irradiation, like dominated regions. And so that means that the water ice has not been amorphized to like greater depths. So because reflectance spectroscopy is probing the very top layers, probably those regions are still crystalline and it's not being converted to amorphous ice completely. So because like even though crystalline ice abundance we're getting is very low, there is still a strong detection. All right. Oh, I forgot to mention that one other sort of improvement that we made in analysis as compared to previous work is that we included certain physical parameters that were otherwise ignored in previous works. So, for example, remember I mentioned very early on in the talk that particle irradiation actually distorts water ice bands and like it kind of shifts it as well. And you can clearly see that in the Europa in this data set, because like S1's 1.5 micron band is shifted with respect to S2 and S3. So previously what people would do would just like sort of to get around this problem, they would just discard the data that is coming from the water ice band. But instead of discarding the precious data, what we decided to do was like have an empirical parameter that kind of shifted the water ice band. So that you don't need to change your abundance to sort of force fit that shift. And this is basically that parameter, result for that parameter. And we got the most amount of shift for S1, as you can clearly see by I, that is what you would expect. And S2 and S3 pretty much showed no shift. So when I'm talking about shift, I mean as compared to like a neutral water ice spectrum. So S1 is the most shifted because it's the most irradiated. So it works well with our expectation. Okay. And we didn't find any evidence for carbon dioxide and sulfur dioxide. And this was, again, expected because if you actually do the simulations, like just of simple water ice plus carbon dioxide or plus sulfur dioxide mixture, you need to go to unreasonably high abundance fraction of the oxide to actually start seeing the sharp features. And even then, they are so sharp that they fall within the resolution limit of the NIMS data. So here the dots present like spectra bind to Galileo NIMS resolution. And so, yeah, so basically it makes sense that we didn't see these features. And sulfur dioxide doesn't even show up at all. So, so in the 1 to 2.5 micron range data, that is basically the bulk of Galileo NIMS data. Unfortunately, carbon dioxide and sulfur dioxide, like the trace oxides, it looks difficult that we'll ever be able to get something out. Okay, and finally, I will sort of conclude with a current project that I'm working on, which uses the same framework, but to answer a question that is of interest because of what we are going to get in the future. So, which is about exploring the detectability of organics on Europa's surface. So, organics have not been detected on Europa. Or like any kind of hydrocarbon signature, because the data, like as I'll show, the data that is their features mostly reside at longer wavelengths where the data is very poor, and so but we are interested in constraining these species, specifically in those in these like dark regions where we think that material is coming from inside, and sort of get further at the subsurface ocean composition in terms of like availability of these kind of molecules. And so the project goals were basically to determine observational requirements. So what is the SNR for spectroscopic data that will enable the detection and characterization of specific kind of hydrocarbon species, organic species. And in doing so, we also wanted to establish a data analysis and interpretation framework basically based on the Bayesian inference framework that I've been talking about, which can help us get robust detections and of these trace species, especially because the data is going to be not very good, and these molecules are spectrally very complex. And which is I'm showing here in these simulated spectra that if you look at the 3 to 5 microns reach, which is where Galileo has not able to give us any data, good data, you see that organics are very spectrally, not well here it's like trace hydrocarbons are very spectroscopically rich. Water ice is on the other hand neutral, and that is true for most of the other bulk components like salts and stuff, that they are, because it's mostly they are attached, there's a lot of water ice attached to it. It's pretty neutral. But the problem here is that the species, they all look good when you look at their individual reflectances, but when you actually account for the expected amount, so like basically an order of 1%. So here I'm showing like reflectance spectra of these trace species mixed with water ice, and you see that their features are pretty much like tiny deviations and dips on top of a water ice continuum. And so when you zoom into the 3.8 to 5 microns region, here you can see that how they are present. So we're looking at features on the order of 1%. And that is basically what we're trying to identify and then detect, and then from that try to narrow down which molecule it might be coming from and what is its abundance and so on.
All right,
And
Ishan,
sorry,
maybe just 2 minutes so there's time for questions.
Oh, sorry. Yeah.
Yeah,
So
no
let me just quickly wrap this up. Like there are like 3 more slides. And so, so I started this project by basically just showing basically just taking a simple case of like hydrogen cyanide, which is hydrogen cyanide is a good sort of test species because it has sharp features, as you can see in this region. And also cyanide features have been detected on the other Galilean moons. And so we just wanted to see what its detectability looks like. And so we simulated, so what I have done is basically I've taken it in a simple background of water ice, and then I've simulated observations of as a function of different SNRs and abundance of hydrogen cyanide. And you can see that in the simulated data, you can still clearly see those features. And when you take these, and so what I'm interested in is like, how much do these features, how strong are these features? So how much do they stand out with respect to the background noise? And so that is what I'm defining as like the sigma significance of the feature. So basically how far out it is from like the average noise. And when you do that for different amount of hydrogen cyanide and different SNR of data, you kind of see that I mean, as expected, for a larger amount of the trace species and larger SNR data, the significance of the feature increases, and especially within the SNR limits of Clippers. So Europa Clipper, this is the next mission to Europa, and this is my spectrometer. We expect that Clipper is going to give us like 3 sigma confidence if you take the threshold. It can detect these features if they are present at like a few % abundance. Great, especially because previous and current facilities are nowhere near capable. But we wanted to see if we can push this detection limit down further, because in like comets, hydrogen cyanide is present at like maybe like a % abundance. So, and that is where the Bayesian evidence approach that I was talking about helps. So it pushes the detection limit down further. And I have alluded to this previously, so I'll quickly skip over it. But the reason it works great is because hydrogen cyanide, like when you remove hydrogen cyanide, like for example, here I'm showing just a water-only model, the residuals are poor throughout across all wavelength regions, because hydrogen cyanide is affecting the spectrum at every wavelength point. So there is minor effects that are missing throughout, and that is what kind of increases the detection significance. And when we do that in the presence of like many species, so here I have showing like a spectrum that is a mixture of 90% water ice and 1% of a lot of trace species, including hydrogen cyanide, at an SNR of expected like Clipper data quality. we see hydrogen cyanide features, but there are overlaps because there are other species that have features at the same wavelength or near the same wavelength. But even then, a Bayesian evidence-based approach helps, increases still is able to detect hydrogen cyanide at a very high confidence. And so this is a paper that I'm going to submit very soon. So keep an eye out for that. And with that, I think I'm going to just quickly end, and I'm going to skip over my last slides because we are out of time. But thank you a lot for listening, and I hope some of this was interesting. Thank you. I'm sorry for running over time.
No problem. Let's thank Ishan. Are there any questions from the audience? Feel free to put it in the chat or just unmute yourself. I had a question, I guess.
Yes.
So you said maybe you have a slide for this. The applications to JWST and exoplanets aren't quite ready, but did you want to, I don't know, summarize what a goal might be there or something?
Yeah. So I had a slide just to sort of advertise the work. So basically what so the left side is some work I did for atmospheric observations, like predicting our inferences from JWST quality data. But you can do something similar with exoplanet surfaces. And the idea here is that James Webb's mid-infrared spectrometer is going to go collect data out to 25 microns. And even though it'll be low resolution, low precision data, it'll still be some spectroscopic observation information, because our only detection so far of a planetary surface has been one Spitzer data point. And that is not enough to get at whether the surface is primarily, I don't know, basaltic versus granitoid or something like that. Whereas if you simulate observations across longer wavelengths, as I'm showing here, the features start to stand out. And a lot of them are at levels where JWST's precision is good enough to tell them apart. And so that is basically what we're doing, where a group in the geology department at Cornell is collecting a lot of lab measurements, basically emissivity of different kind of rock types. And what I am doing is taking those emissivity measurements of those rocks and converting them to simulate to exoplanet observations. So imagine a planet covered with this one rock type, what would it look like? And then now we are at a stage where we are basically adding noise to these spectra, so with expected JWST precision, and seeing how does that affect, are we still able to tell bulk rock types apart, and what are the the parameters that can detect observations, how many transits would you need to improve your detection versus so those that kind of work.
Really cool. Thank you. Are there any other questions? Maybe you also, go ahead.
I'm no, sorry. There were a couple of messages from the chat, but they're just thanking. Well, you're very welcome, and thanks for this.
I saw maybe you had a slide about the job market. If you want to flash that up, I just have some.
So I kind of brushed over it, but this is something that I've been showing in a lot of my talks, where basically, I'm set to graduate towards the end of the summer, but I'm still in the job market looking for stuff. So if any of this interests you, and or you think that there's an application to your work, because it's very broadly applicable to different physical models and different kind of data sets, I'd be happy to chat. So do send me an email, or even if you're just interested in chatting about this work or the rocky exoplanet surfaces work in a more informal way, I'll be happy to.
Great. It's the top of the hour, so let's thank Ishan again, and I think we'll stop there. Thanks very much, and we'll see you next time, everybody.
Yeah, thanks, Allison. Thanks for inviting. Yeah. Bye-bye.